So we are going to spend some time talking about the multiplicative ergodic theorem of oscillators. So the setting is the same that we have been using. We have a transformation, an invariant probability measure, then we have a map from M to GLD. And we consider the skew product defined by x, v goes to f of x, gx of v. And I need some notation, a flag in RD is a finite sequence of subspaces. Subspaces V1, V2, Vk. V1 is RD, and then the sequence must be decreasing, strictly decreasing. Each subspace is strictly contained in the previous one. In principle, the dimensions can be any as long as they are decreasing. We say that the flag is complete if this space has dimension d, this one has dimension d minus 1, d minus 2, etc., all the way up to dimension 1. But here I'm not assuming that the flag is complete. So the multiplicative ergodic theorem says that there exists, let me state exactly the way it is in the book. So assume that the positive part of the norm of A and the positive parts of the norm of A inverse are integrable. With respect to mu. Then the statement is that there exists for mu almost every point there exists a flag so RK equals V1 x Vkx and numbers lambda 1 x bigger than lambda 2 x bigger than lambda kx such that first of all, all these objects are invariant. So Ax of Vi x is equal to vi f of x, and lambda I of x is equal to lambda I of f of x. This is for every I, and mu almost every x. Okay? So these objects are, so please be careful. This means these are real numbers, and this means bigger than, and these are vector subspaces, and this means that this contains this, strictly. Okay? I'm using the same symbol. The second property is that the maps x goes to lambda I of x, vi of x, and x goes to lambda I of x are measurable. Not continuous, measurable. Actually, it doesn't make sense to, I'm not assuming that M has a topology, so it wouldn't make sense to, would not make sense to assume, to speak of continuity. But what we have is that these maps are measurable. And the main property is the last one. It says that if you look at vectors vi in vix minus vi plus 1x, so in the difference between two consecutive subspaces in the flag, then, and you iterate those vectors, then this grows, the norm grows like e to the n times lambda I of x for n large. So the growth of the iterates of a given vector, so for any vector vi in the difference, the growth depends only, is given by the corresponding number lambda I. So the precise statement is that the limit 1 over n log of the norm exists and is equal to lambda I of x. Okay? So this is the statement of the multiplicative ergodic theorem of Oscillides. Now, there are two things that I have to make a little bit more precise. The first one is that the number k that appears here depends on x in general. So depending on the point, the flag can contain a different number of subspaces. So this is Rd. Yeah. This is k of x. Of course, k is necessarily smaller or equal than d. So the numbers, the possibilities for k are finite. It can be 1, 2, all the way up to d. But in principle, this can depend on x. Then I have to add that this k is also invariant. And is also measurable. And that's it. Okay. The norm is irrelevant here. If instead of the operator norm you use a different norm, it is irrelevant. Under this assumption, it doesn't really matter. If the new norm also is integrable, then it doesn't really matter. The other thing that I think I have to explain is what means this statement. What does it mean to say that a map that assigns to each point a vector subspace is measurable? Okay, that I have to explain here. Given a map X, V of X, where V of X is contained in Rd, is a subspace of Rd, we say that it is measurable. Such a map is measurable if, well, the short definition is the following. If you can find a basis for the subspace Vx such that the elements of the basis are measurable vector fields. Okay, that's the definition. But there's a little technical problem here, and that is that I'm not saying that the dimension is constant. Okay, so I have to be slightly, say one or a couple more sentences. So if first condition for any L between 1 and D, the set of points X such that the dimension of Vx is equal to L is a measurable set. Set of points X in M, where the dimension is constant equal to L, is a measurable set. And the other condition is that, let's give a name to this, EL, for every L, there exist measurable maps from EL to RD. Let me call them XJ. Okay, this we know what it means. Here J goes from 1 to L, such that if you take those vectors x1 of x, xl of x, this is a basis for the subspace Vx at every x. Okay. So a vector bundle, a map that assigns to each point a subspace of Rd is measurable if you can find a basis formed by measurable vector fields. Okay, and that's what this means. Now there are other ways to present the definition involving the Grassmannian manifold, but they are equivalent to this. Okay, so these numbers are called Lyapunov exponents. Lambda 1, lambda k are the Lyapunov exponents of f mu f at x, and v1 vk is called the Ocelladets flag of f at x. Now we already used the expression Lyapunov exponents before with the different notation, so I have to say a little bit more to connect the two notions. It is part of the proof. It is part of the proof that lambda 1 of x coincides with lambda plus of x, and lambda k of x coincides with lambda minus of x. And that is the reason why these two numbers are called the extremal Lyapunov exponents. This is the largest exponent. This measures the growth of the norm of the matrices. This is the smallest exponent, measures the growth of the conorm. And the other exponents measure growth of iterates of different vectors in between. And we have this flag type stratification of the intermediate behaviors. Okay. I'm going mostly to talk about that theorem, but there's a second theorem of Facilides that is more restrictive but has a stronger conclusion. So same assumptions. Plus, suppose that f is invertible. This is perhaps a more popular version of a statement of the theorem. Suppose that f is invertible. Then, of course, all this is true. This is a special case. But we can say more. Instead of saying, then for mu almost every point, there exists a splitting of RD into subspaces and numbers, the same numbers. So I'm not going to write, such that first condition is invariance. So AX of EIX is equal to EI f of x. And VIX is VI plus 1x direct sum EIX. The second condition is that the map sending x to EXI is measurable. And the third condition is that the limits 1 over n log of a n x vi is equal to lambda I of x. And here we can take limit both in the future and in the past. Same exponent both for the future and the past. Yes. Okay, so what is, I'm still going to add one extra property, but what is the main difference between the two statements? In the non-invertible statement, we have, say, we have a flag. So we have V1 equals, say, R3. Then inside this V1, we have, say, a plane, V2. which is a plane. And I'm going to draw the case of a complete flag. And then inside this plane V1, we have a line V2, okay, like this, V2. And then inside V2, we have the trivial subspace at the origin. Okay? So this is what the non-invertible theorem 1 gives us. There's V1, that is the whole space, then V2, and then any vector that is in V1 but not in V2 grows at the exponent lambda 1. Any vector that is in V2 but not in V3 grows at rate lambda 2. And any vector in V3 minus 0 grows at rate lambda 3. Okay, we have this stratification, and the difference vectors in the difference between consecutive subspaces have a well-defined rate of growth. Now, what is the difference here? The difference is that we can find a subspace that is invariant that corresponds to the difference. So in addition to V2, we also have a certain subspace transverse to it that is E1. And then we have a subspace inside V2 but transverse to V3, and that's E2. And then we have E3 is just V3. And then if we, for example, we take a vector in this E1, well, E1 is in V1 but not in V2. So when I iterate forward, any vector here will grow at rate lambda 1 as I iterate forward. But this theorem says that it also grows at rate lambda 1 when I iterate backwards. Okay? And any vector that is in V2 but not in V3 grows at rate lambda 2 in the future. That holds in particular for vectors in E2. But these are special in that if you iterate backwards, they also grow at rate lambda 2. Okay? That's what we get here extra, that there is an invariant transverse, an invariant difference between Vi and Vi plus 1. And then for vectors in this difference, in this invariant subspace, the rate of growth in the future and the past are the same. Okay? And this is a splitting. This is a direct sum. In general, these subspaces are not orthogonal. There's no reason why they should be orthogonal. So the angles can be small. The angles between them can be small. And in fact, in general, they can be arbitrarily small. The angle between E1 and E2 can become arbitrarily small. And that's very bad, because when you have a splitting, you like to think that it's orthogonal so that you can decompose and somehow reduce analyzing what happens in here to what happens in each one of the factors. So it's really nice that although the angle can be arbitrarily small, there is a lower bound that one can give. The lower bound goes like this. Take the angle between any sum of subspaces, EI, and any other sum of subspaces. Okay? So I and J are disjoints. Okay? Take a bunch of these subspaces, take them all together. Another separate bunch of these subspaces, take them all together, calculate the angle at a certain point x. Now, do better than that. Do that for every iterate of x. Okay? What I'm going to write here says that this is bigger than e to the minus n epsilon. So, what does this tell? It tells us that the angle is positive, but that's okay. I mean, it's a splitting. The angle is positive. It tells us that maybe the angle goes to 0 when n goes to infinity. Okay, maybe. And in fact, that happens. But it tells us that it doesn't go to 0 very fast. It goes to 0 slower than an exponential with very small exponents. And here epsilon is arbitrary, any epsilon. And then for n large, this is true. So how do you write this in a simple formula? You say that the limit as n goes to infinity plus or minus of 1 over n log of the angle is 0. So as you iterate forward or backward, these subspaces could start to get closer and closer, but they will be, that will happen slower than any exponential. So this is called sub-exponential decay of angles. And for many purposes, it is just as good as saying that the angle, the subspaces are orthogonal. Not quite as strong, but it's good enough for many many applications. Okay. Now, when I was writing the book, I had a little attack of scruples. Because angles are not numbers. Angles are not real numbers. Angles are, what is an angle? Angles go from 0 to 2 pi, and 2 pi equals 0. In the real line, 2 pi is not 0. It's only in classroom that 2 pi equals 0. So what this means is that an angle is really an element of the circle. It's a point in the circle. And we could discuss for a very long time whether it makes sense to speak of the logarithm of a point in the circle. That is the reason why in the book I always write log of the sinus of the angle. Okay? But I'm not going to do that in classroom. I'm going to pretend that angle is a number. We only deal with small numbers, and for small numbers we can identify the number with the angle. Okay? Okay, so what I'm going to do today, and certainly on Thursday, perhaps even next week, is to give a proof of this theorem. Then there's a little extra work that has to be done for theorem 2, but it's not very hard. So I will, in classroom, I will focus on this theorem. The proof that I'm going to use to present is due to Peter Walters. Basically due to Peter Walters. And in the non-invertible case, and then Jairo Bocchi wrote a presentation of Walters' book, Walters' proof, and extended it to the invertible case. The advantage of this proof is that it uses ideas from dynamics instead of just linear algebra. And the other advantage is that the main role is played by invariant measures. So somehow the proof connects with things that we are going to talk about next. There's something very deceiving about the proof of this theorem, which is that it is very easy to prove 95% of the theorem. And then we have to work hard to get the other 5%. Okay, so let's do the 95% first. So for each x in M and V in RD, we are going to define lambda xv to be the lim sup as n goes to infinity of 1 over n log a n x v. The 5% that is really hard is to prove that the limit exists. Working with the lim sup is as easy as we are going to explain. So then there's a little lemma. For any x and any real number c, the set of points, the set of vectors v such that lambda xv is less or equal than c, the set of points where the growth rate is bounded by c is a subspace, is a vector subspace of RD. Okay? Now I'm not even going to write the proof because the proof is immediate. First of all, if a vector v belongs in this set, if you multiply v by a constant, if you multiply v by a scalar constant, what happens to this constant? By linearity, the constant comes here. Due to the properties of the norm, the constant comes here with absolute value. So you have logarithm of the constant multiplied by this. The logarithm of a product is the sum of the logarithms. So you split this into two terms. One is this, and the other one is 1 over n logarithm of the constants. And then this term goes to 0 because you are dividing by 1 over n. Okay? So if v is here, any multiple is here. What about the sum? Suppose you have two vectors v1 and v2 and they are here. Let's look at the sum. The sum you have to write v1 plus v2. By linearity, that is the sum of an of x v1 plus an of x v2. The norm is subadditive. And then you play with properties of the logarithm and you conclude that, so lambda, what I'm saying is that lambda of cv is equal to lambda v, and lambda of x v1 plus v2 is less or equal than the maximum between lambda x v1 and lambda x v2. Okay, and if you have these two properties, then the lemma is an immediate consequence. The properties are actually written as exercises in the book. Okay, so we have this lemma. For any constant c, this set is immediately a vector subspace. So what we are going to do is to take all possible values of c and look at this space. Let's call it E sub C. And let's look at this. Here is C and here is EC. So this is a function that associates to each x the corresponding subspace. And you see, as C grows, this condition becomes easier to satisfy. So the function C goes to EC. I don't want to call it EC. I want to call it VC. This function is VC, is non-decreasing. Okay? If C is bigger, then the subspace cannot be smaller. So the picture is something like this. Oh yeah, and of course, the dimension of VC is an integer number between 0 and D. So as you vary C, you get a certain number of vector subspaces growing, at least not decreasing. Of course, the dimension is also non-decreasing. And so you have only a finite number of possibilities. So I'm going to call V1 of x, V2 of x, Vk of x are the values of this is Vc of x, of course. The possible values of Vc of x when C varies in R in decreasing order. Okay? In principle, this is a function from R to subspaces of Rd, but since this is a non-decreasing function, it can only take a finite number of values, and these are the numbers Vx1, Vx2, etc., Vxk. Okay? And then I call, so take, and this tells you exactly how you construct the Oscilladets flag. It's already there. But take also lambda I of x to be lambda of x v for any v in Vxi minus Vxi plus 1. So just choose any vector between these two, between consecutive elements of the flag, and call that lambda I. Now, of course, I have to explain that this does not depend on the choice of V in the difference, right? I'm saying here for any V in the difference, I have to explain that it does not depend on which vector I take in the difference. Why is that? Suppose it depended. So this is vi, and inside here you have vi plus 1. I'm going to draw a picture where vi has dimension 3. No, this is vi. And then vi plus 1 is a line. Okay? Suppose this depended on which vector I take. So suppose there was some vector v1 and vector v2. There were two vectors, v1 and v2, such that lambda x v1 is not the same as lambda x v2. I'm claiming that it doesn't matter which vector I take, because they all have the same lambda. Suppose that was not true. Okay? For example, v1 has smaller lambda than v2. Then I could choose C in between. So choose C between these two. And since those two vectors have different growth rates, there would be Vxc would be contained in Vi and containing Vi plus 1. So there would be some value of this function for some value of c that is in between Vi and Vi plus 1. And that is a contradiction, because these are the values, the possible values, all possible values of Vcx. Okay? So you see, very rapidly we already have, and somewhat disappointingly, we already know what is the oscillators flag, and we already know what is the who are the Lyapunov exponents. And some of these properties are already automatic. What have we done so far? What have we proved of the theorem? We proved this with lim sup. Okay, as I already warned, the real difficulty is to pass from lim sup to lim, but that's what we are going to do later on. We already have this and this, in fact. Okay. So observe that lambda of x v is the lim sup of 1 over n log a n of x v. Okay. This is the lim sup 1 over n log of a n minus 1 f of x ax of v. Okay, it's just definition of what means a n of x. This is the multiplication of the values of a on the orbit of x, so I can decompose in this way. This is the same as lim sup 1 over n minus 1 log of a n minus 1 of f of x ax of v. It doesn't make any difference whether I divide by n or by n minus 1 as n goes to infinity. And this is, by definition, this is lambda at f of x of the vector ax of v. Okay. So you see, this formula tells us that the values of lambda x for different values of v are the same as the values of lambda of f of x for different values of the vector here. Okay. This implies part A of the theorem, that the lambdas are the same, the values of this function are the same at x or f of x, and the places where the vectors for which this growth is less than a given constant are the same. We are preserved by iteration. So we already have this, and we also have this for lim sup. So what I'm going to do next is to talk about B, part B, measurability. That's not a difficult part of the argument, but it's not entirely trivial to prove that these objects vary measurably. We somehow have the general principle that all functions are measurable. But to prove that these functions are measurable requires a little bit of technology. In particular, it requires two theorems that I'm just going to quote, abstract theorems from measurable theory that I'm just going to quote. Okay, so here is the first theorem. This is called the projection theorem. So let x be complete, separable metric space complete metric space, complete measure space, probability space, probability. I will explain the keywords. Probability space, and Y be a separable metric space. Be a complete separable metric space. Let phi from x times y to x be the canonical projection. So the theorem says that if E is a measurable subset of x times y, then phi of E is a measurable subset of x. So the way to remember this theorem is the following. If you have two spaces that are not too nasty, x and y, then when you take a measurable subset of the product and you project, the projection is still a measurable subset. Okay? So explaining the key words, complete here means that if A is contained in B and measure of B is 0, then A is measurable, and of course the measure of A is 0. Okay. Complete probability space is a subspace where any subset of a set of 0 measure has 0 measure, is measurable. Okay? Complete here means something completely different. Means that every Cauchy sequence is convergent. Separable means that there exists countable dense subsets. Countable exists countable dense subset. This countable subset dense in the space. Okay, and this is that every Cauchy sequence is convergent. There's only one last thing that I have to say, and that is what it means to be a measurable subset of the product. Okay, the set of measurable, the sigma algebra of measurable subsets of the product is, by definition, the sigma algebra generated by sets A times B with A measurable in X and B measurable in Y. Okay. When you have two measure spaces, you can construct the product by doing the following thing. You take any product of two measurable subsets of the two subspaces, and you consider the smallest sigma algebra that contains all those subsets. Okay? Observe that if E is a product, then of course the projection is A, which is measurable. But what I'm saying is that any measurable subset, any element of the sigma algebra projects to a measurable subset of X. Okay? This is not a trivial statement. Projection theorem. And the other theorem says so let M be a complete matrix, a complete probability space, Oh, by the way, I didn't say it, but when I define a complete probability space, so this is a definition, that any subset of a set with zero measure is measurable. It is a simple fact that if you give me any probability space, I can always complete it. What do? I just say that any subset, any subset of a measurable subset with zero measure is measurable. Right? I add those objects to the sigma algebra. I take the sigma algebra generated by that. I extend the measure in the obvious way. So given any probability space, you can always complete it for a given measure. And so this is not really a restriction. So given a map X to Vx, where Vx is a subspace of Rd, the following are equivalent conditions. The following are all equivalent. The map X to Vx is measurable. The graph is a measurable subset of M cross Rd. This is really nice. I already explained what it means for a function like this to be measurable. It means that you can find bases formed by vectors that depend measurably on the point. And this theorem characterizes when that happens. The function is measurable if and only if its graph is measurable. If and only if its graph is a measurable subset of the product. And it gets better. No? No, that's okay. That's all we need. Okay? That's all. So let me explain how we can use those two theorems to prove part B of oscillators. Okay, so choose any basis E1, ED of RD. For example, the canonical basis. It doesn't really matter. An arbitrary basis of exercise. Lambda 1 of x is the maximum of all lambda x ei, I from 1 to d. So remember, lambda 1 of x is the largest value. So by definition, this is the maximum of lambda x v over all v. The exercise says that if you take the maximum over a basis, you already obtain the maximum over all v. Why is the exercise easy to believe? Because every vector can be written as a linear combination of the elements of the basis and blah, blah. Okay? You relate the two maxima easily. So this is easy to believe. Okay. Now, the function, I didn't say it. Where is it? Let me remind you. The function lambda x v was defined as a lim sup x, lim sup on n, 1 over n log of an of x v. Okay? And this, by construction, is a measurable function. Function of x and v. Okay? Everything here is measurable, and we have lemmas that tell us that if we have a sequence of measurable functions and they take the lim sup is still a measurable function. Okay? So any of these this function is measurable. And so if I take the maximum, lambda 1 of x is a measurable function of x, because it is the maximum of a finite number of functions. Each one of them is measurable. Okay? If I were taking the maximum over all v's, that would be more complicated, because that would be a maximum over a continuum of functions. But since this is just over a countable set, the result is still a measurable function. Okay? Now, v1 of x is the set of vectors such that lambda x v is less or equal than lambda 1 of x. This is not, yeah, it is true. Okay? Well, this is not very interesting because this is RD. Okay. What is interesting is that v2x is a set of vectors such that lambda x v is smaller than lambda 1 of x. Okay? I'm going to claim that this varies is a measurable function. I'm going to use this criterion to prove that v2 is measurable. So how do I do that? So my claim is claim. The map assigning to each x vx2 is measurable. Okay, proof of the claim. I'm going to look at the graph. The graph is the set of x v such that v belongs to vx2. In other words, it's the set of points x v such that lambda of x v is smaller than lambda 1 of x. This is a measurable function. And this one is also measurable, as I explained. So the set of pairs where this one is smaller than this is a measurable subset. So the graph is a measurable subset of M cross RD. The M cross RD. Then by this lemma, by theorem 2, from B, so the graph is measurable, so by theorem B, we get the conclusion. Okay? Essentially, this is the argument I repeat to prove that V3 is measurable and so on. But I have not been very careful. I have to be more careful. This is correct, but I have to insert things in between. And the reason is that the number k depends on x. And it could be that k is equal to 1. And then if x is such that k is equal to 1, it makes no sense to speak of V2. Okay? So I have to say something in between that. I have to say something in between that. Here. There's something missing. So let us look at the set of pairs, that same set. Now this set I'm going to call V2 star. It's the same set I wrote there. So, as I explained, this is a measurable subset of M cross RD. Okay? Let's try to draw a picture. Here is M. Here is M cross RD. Here is RD. And then, you see, depending on the point X, it could be that V2 star, it may happen that V2 star intersects the vertical over X or not. Okay? So I have a set here. Maybe it intersects this vertical, maybe it does not intersect the other vertical. So I'm going to look at the projection of this set. The projection here, downstairs. So what is the projection? It is the set of points X in M such that this inequality holds for some V. Right? I have this set V2 star here. I don't know how it looks like. I don't know much. If there is some vector here, then x is in the projection. If there is no vector of v2 star, then x is not in the projection. Okay? Now, what does it mean that x is not in the projection? It means that there exists no vector v where lambda is smaller than lambda 1. In other words, it means that for all v, if x is not in the projection, that is the same as saying that lambda x v is equal to lambda 1 for all v. Okay? And then you look at the meaning, the way we constructed these lambdas, these lambda 1, etc., lambda k, they are the possible values of this function when v varies. So if all vectors give the same value, that means there's only one value possible. It is the same as saying that k of x is equal to 1. Okay? So pi of v star 2 is precisely the set of points for which k of x is at least 2. Okay? For the other points, for the points where k is equal to 1, I don't have to do anything. I only have one subspace, that is v1, that's the whole space. I don't have to do anything. This is where I have to work further. And by theorem A, by the projection theorem, this is a measurable set. Okay? So here we take x in pi of v2 star we take x in pi of v2 star, then for such points this is non-empty, and that's where this is a subspace, and that's where we prove that we have measurability. Okay? The points for which k is equals 1, we don't have to do anything anymore. It's already done. Okay? So you see, we use both theorems. Let's do one more step, just to see that that's all we need. Next. Let v star 3 be the space, the subset of pairs such that lambda, oh, before that, wait. Before that, before that, so for x in that space, that set, let E1 of x, EL of x be a basis of x of v to x. I'm going to repeat from here. So choose a basis. Then, if you want, exercise. Lambda 2 of x is the maximum of lambda x ei of x I from 1 to L. And this is a measurable function of x. Then you let v3 star be the set of pairs such that lambda xv is less than lambda 2. This is a measurable subset of the product. So the projection is, which is the set of points where k is at least 3, is a measurable subset of M. And then for x in this projection, let's we have vx3, v3x equals the set of points, the set of vectors in RD such that lambda xv is less than lambda 3, less than lambda 2, sorry. And then we have the corresponding claim that this map is measurable. And the reason is the same, because the graph is equal to v3 star is measurable, etc. Okay, so here I'm using theorem A, the projection theorem, and here I'm using theorem B. Okay. So at each step, we restrict the domain. In this case, to pi over v2 star. The next time to pi over v3 star, and so on. We restrict the domain. The new domain is measurable because of theorem A, and on that domain, the bundle is measurable because of theorem B. And in the process, we also prove that the lambdas are measurable. Now, I cheated a little bit here, because the dimension of this subspace may depend with x. Okay, so what we have to do is, first of all, to decompose my domain into subsets according to the dimension. And then on each one of these subsets, I choose a basis with a given dimension. The choice is irrelevant. And by definition of what we know already, that this is measurable, this is a recurrence argument. Since we already know that v2x is measurable, I can choose a basis where these vectors are measurable. The first time the basis is constant. From the second step on, it depends on x, but it depends on x in a measurable fashion. So it doesn't matter. Okay? But I did skip one step. In the book, it's written with the details. I skipped one step where you first have to break this according to the dimension of the v2. But at each, these decompositions are only in a finite number of subsets. Okay? So it's not entirely obvious how to prove measurability, but once you have theorem A and theorem B, it becomes just a little machine repeat this argument. And it is a bit more delicate because of these dimensions may vary, but there's nothing very profound there. Okay, so you see this is 95% of the theorem. We proved A, we proved B, we proved C with lim sup. The goal now is to prove that actually the limit exists. And that's all that's missing. I'm going to tell you what the idea is, and then we'll have to work to implement this idea. So now we go from lim sup to actual limits. Now, the idea is the following. Let's go back to a much simpler situation. Okay? Suppose you have a function phi from m to r, bounded function. And for some reason, you decide to look at the sums of this function over the iterates of a point x. And in fact, so you look at the sum, and you look at the average. Okay? You look at the average of the function over the first n iterates of a point x, and then you make n go to infinity. And of course, you can define S phi of x to be the lim sup of this. And you can define I phi of x to be the lim inf of the same. Okay, and since I assume that the function is bounded, of course the lim sup and the lim inf exist and are finite. But then a miracle happens, and the miracle is that S phi of x is equal to I phi of x for almost every x. With respect to any invariant measure, F invariant measure. Well, I'm not stating anything new. This is the ergodic theorem. What I'm stressing here is that in ergodic theory, miracles can happen, and basically ergodic theory exists because if you want to talk about almost every point with respect to an invariant measure, then the behavior of almost every point is much, much better than the behavior of any point. Almost any point tend to have a well-defined behavior. For example, in this simple situation, this elementary situation, the limit actually exists. Okay? So the way we are going to go from lim sup to lim is by using this idea. We are going to introduce invariant measures in the appropriate place, and we are going to use some version of the ergodic theorem to prove that where we wrote lim sup, the limit actually exists. Okay? We're going to use the miracle of ergodic theory. Now, how do we do that? I have to so I'm going to erase this, and you keep in mind that everything we want now is to prove that this limit exists. So for simplicity, I'm going to write P to mean the projective space of Rd. And in fact, what I'm going to say in the next few minutes is true for any compact metric space. Okay. And the yeah. Okay, so here is the proposition. Let G P be a skew product, be a measurable map of the form G of x v equals f of x, and then gx of v. So this is a skew product because the first component here only depends on the first coordinate. Where this gx is a map from P to P. It's continuous. Gx from P to P is continuous for every x. So what is the map that we have in mind? We have in mind the map G from M to P R D to M to P R D, that to each x and v associates f of x and then ax of v. The projective cocycle associated to that. This means this represents the line through a given vector v, an element of projective space, the line through a given vector v, and this is the image line under the matrix A of x. This is the G we are interested in, and it's clear that the action A may not be a continuous function of x, but this is a continuous function of v, because A is a matrix. Okay? I'm not saying that these things vary continuously with x. I'm saying that they vary continuously with v. So for any function phi, I'm going to introduce this space. For any function phi in a good space, I'm going to define precisely. Let I of x be the lim inf 1 over n sum j from 0 to n minus 1 phi g I gj x of v, and let s of x be the lim sup. Well, actually, it's not correct. This is not what I want to write. I want to write this here. So I want to write the limit of 1 over n infimum over x of this. And here I want to write limit 1 over n supremum over x. This. Not over x, over v. Thank you. Over v. Okay? The proposition says both limits exist mu almost everywhere. And there exists G invariant probability measures eta I and eta S such that the integral of I d mu is the integral of phi d eta I, and the integral of S d mu is the integral of phi d eta S. Okay. So this is a key step in the proof of going from the lim sup to the limits. I'm probably not going to try to start the proof of this proposition today, but let me, so that we don't get lost, let me keep reminding what are the characters. This is an abstract statement. Okay, P is any compact metric space, G is any skew function, a skew product, and phi is any function. I still didn't say what F is, but this is the P we are interested in. This is the G we are interested in, and the phi we are interested in is the following function. This is a very natural function. Logarithm of AX applied to V divided by V. This is the phi we are interested in. Okay? So these boxes that I'm highlighting in blue are the applications, the application we have in mind. This is the application we have in mind. Okay. So instead of going to the proof, let us look at what is written here and try to interpret what is written here. What does it mean, the sum of phi calculated at g, j, x, v? What is this? Because this is absolutely crucial to understand how the proof goes. So what is this? We have first to understand what is g, j of x, v. Well, g is here. So this is the sum, j from 0 to n minus 1, of phi calculated at, what is g, j of x, v? Well, it's f, j of x, and then is a, j, x of v. Just iterating. Maybe I should continue to use my notation. V here is a projective class, is a real line. And this is okay. When I write this, this means the real line through the vector v. It's an equivalence class where I consider two vectors equivalent if they differ by a factor. Okay? And the factor is irrelevant there. This is well defined. Okay? Now, what is this sum, this big sum? Well, by definition, is the sum of the logarithm of a of fj of x applied to a j x of v divided by a j x of v, by the definition of phi that is written here. Okay? So this is the same as the sum from 0 to n minus 1 of the logarithm of what is written upstairs. We have the first j iterates of a, and then we have the next one. By definition, what is written upstairs is a j plus 1 x of v. And downstairs, a j x of v. This is a very clever idea. This sum, this is a Birkhoff sum of the function phi with respect to a certain dynamical system G. This is a Birkhoff sum, but when you spell it out, it turns out that the terms here are just a certain sequence at time j plus 1 minus the same sequence at time j, because logarithm of the quotient is the difference of the logarithms, so we have a minus. So you have this telescopic property. Okay, and then this simplifies, suddenly this simplifies, and you get log of an x v minus log of v. Okay, so now that we realize this, there are many things that we can see. For example, the limit 1 over n sum j from 0 to n minus 1 of phi g j x of v is the same thing as the limit of 1 over n log of anx of v. Right? This term here dies when you divide by n. So you see, we want to prove that this limit exists. We don't know that. But that is the same as proving that that Birkhoff average converges. So that's where I'm linking the statement in Nassier-Ledetz's theorem with the Birkhoff ergodic theorem. Proving that so what we know at this point, unfortunately, is that the lim sup exists. And this is lambda of xv. So to prove that this is a limit, what we have to do is to argue that this limit here exists. And that's where the ergodic theorem is going to help us. Okay? So this is one observation. And to finish, I want to comment on what is written here. I want to comment on what is written there. So another observation is the following. What is the sup over all v of the sum of phi g j x v? What is the sup? Okay, my P is the projective space. When I take the sup here, what is that I have? Well, for the same reason as before, this is the sup over all V of that formula. Right? So what is the supremum of this quotient when we vary V? Well, we know what that is. It's the norm of an of x. It's the operator norm. So this is precisely the logarithm of the operator norm of the matrix. Okay. By the way, if you take the infimum, for the same reason, if you take the infimum, then you get the logarithm of the conorm. Okay. So you see here and here, what I'm really looking at is the log of the norm and the log of the conorm of the sequence. And now you already know why both limits exist, because you already know the Furstenberg theorem. Furstenberg theorem says that the limit when n 1 over n log of the conorm and limit 1 over n log of the norm converge almost everywhere. Okay? The only reason why this is not exactly the Furstenberg theorem is that we are stating an abstract result. Okay? But you already guessed what is the proof by, and I will do that next time, by subadditivity. these sequences here, this one is sub-additive and this one is super-additive. So that's why the limit exists. So we are going to prove the deep part of the Oscillides theorem. We are going to prove it using the sub-additive ergodic theorem. And the way the sub-additive ergodic theorem comes into the picture is explained here in the case that we are interested in. Okay, I think that's enough for today. Next time I will restate the proposition and we'll move from there. Oh, I'm sorry. Yeah, I'm sorry. I forgot that. Yeah. Thank you very much, Dmitry. So, yeah. I was planning on starting with that, and then I forgot. So, lemma 1 and lemma 2. Let phi be an integrable function. So this refers to something that I didn't complete last time when I was proving the sub-additive ergodic theorem. Okay, I was proving using a lemma. I proved the lemma using the Birkhoff ergodic theorem, and I had promised I would not do that. So let me come clean with you. Let phi be an integrable function. Then 1 over n phi f n of x goes to 0 for mu almost every x. Lemma 2. Let phi be I actually already corrected the text, but I'm not sure that I uploaded it on the web. Be a measurable function such that psi equals phi composed with f minus phi is integrable. Then then 1 over n phi f n of x converges to 0 for mu almost every x. So these are two statements. And here are some observations about the statements. One of the lemmas implies the other. What is the best of the two? Conclusion is exactly the same. So you have to look at the hypothesis. If phi is integrable, then phi composed with f is also integrable with the same integral. So the difference is integrable. Okay? So this assumption is stronger than this one. If this assumption is stronger, this lemma is stronger. So lemma 2 implies lemma 1. Okay? It has a weaker assumption. And so it's a better lemma. So this is the first observation. The other observation is that they are both useful. Both are useful. Believe me. Third observation, the good one, lemma 2, follows from the ergodic theorem. That's what I started to do last time. But let me remind you what the argument is. You take C calculated at fj of x, j from 0 to n minus 1, 1 over n. The ergodic theorem, Birkhoff, the ergodic theorem, implies that this limit exists almost everywhere. Okay? The ergodic theorem only assumes that the function is integrable. We have that. So this limit exists. But this limit is by the telescopic property is the same thing as the limit of 1 over n phi composed with fn of x minus phi of x. Okay? And this is the limit 1 over n phi fn of x. Okay? So this is the proof. I'm proving lemma 2 using the ergodic theorem. I don't know how to prove lemma 2 without using the ergodic theorem. Okay? I'm not done with the proof yet. The only thing I proved is that this limit exists almost everywhere. This exists almost everywhere. On the other hand, if I look at the set of points where 1 over n phi fn of x is bigger than epsilon, I'm going to write minus 0 here just to stress that I'm looking at the difference between the sequence and my candidate as the limit. This set here, if I calculate the measure of this set, is, so I'm looking at how many points have a sequence that is far away from 0. This is the same thing as the measure of the set of points where, you just do the calculations, where, sorry, no, it's okay. It's okay. Where phi fn of x is bigger than n epsilon. Which is the same thing as mu of the nth pre-image of the set of points y, such that phi of y is bigger than n epsilon. Okay. This is the set of points x that fall into this after n iterates. And since mu is f invariant, this is the measure of the set of points y such that phi of y is bigger than n epsilon. And when I increase n, these sets here decrease. Okay? So the limit, so this measure converges to the measure of the set of points that satisfy this for every n. The set of points that satisfy this for every n is the empty set. Okay? When you have a decreasing sequence of sets, their measures converge to the measure of the intersection. Intersection is the empty set. So this converges to 0. In other words, what this means is that the sequence 1 over n phi composed with fn converges to 0 in measure. In measure. What does it mean to converge in measure? It means what I just said, that the measure of the set of points where the difference is bigger than epsilon goes to 0 for any epsilon. Okay? So this sequence converges almost everywhere to some limit. Let, I don't know, C be the limit. You don't know what the limit is, but you know that the limit exists. And it converges to 0 in measure. The two convergence properties are related. 1 over n phi composed with fn converges to xi almost everywhere, implies that it converges to xi in measure. There are many notions of convergence for sequences of functions. Measure convergence is the weakest one. So if the sequence converges almost everywhere, it converges to the same limit in measure. Okay? But so we have that the sequence converges to xi in measure, it converges to 0 in measure, and the limit is unique. So xi is equal to 0. By uniqueness. The limit in measure is also unique. So 1 over n phi composed with fn converges to 0 almost everywhere. Now you must be slightly disappointed because I promised I would not use the ergodic theorem, and I'm still using it. But the point is that I used the ergodic theorem to prove lemma 2. And what we needed at that point was lemma 1. Lemma 1 is all we need for the subadditive ergodic theorem. This one, lemma 2, is necessary for the Ocelides theorem, which is the reason why I put it. But for the subadditive ergodic theorem, this is enough. And it can be proved without Birkhoff. And it can be proved without Birkhoff. So let me explain how. So let EK be the set of points x such that 1 over k, En, 1 over n phi Fn of x is bigger than epsilon. given any epsilon. Consider the set of points that where the sequence at time n is bigger than epsilon. Okay. Mu of En, it's a similar calculation to that one, is equal to the measure of the set of points y such that phi I is bigger than n epsilon. Okay? Claim. The sum of the measures of these sets is finite. These sets, the measures go to 0. That's what I explained here. The measures go to 0. But now I'm saying that if you have this stronger assumption, not only they go to 0, but the series is summable. Okay? So let us accept this for a little while. The sum is finite. Let E be the set of points x such that x belongs to En for infinitely many values of n. Okay? I'm going to make two observations. First one, x is in E if and only if the lim sup of 1 over n phi of fn of x is bigger than epsilon. Okay? Maybe I should adjust things a little bit here. Let me write bigger or equal than epsilon here. So x is in E if and only if the lim sup is bigger than epsilon. Second observation. E can be written. How do you write the definition of E in a formula? To say that a point belongs to En for infinitely many values of n is the same thing as saying that if you look only at n's bigger than k, then your point is in there for any k. By the way, this is sometimes represented as lim sup. This is just a notation, but lim sup of n, of En. Okay? So the measure of E is this intersection. It is less or equal than the measure of this union for any k. and the measure of the union is less or equal than the sum of the measures, and since that sum is finite, this goes to 0 when k goes to infinity. So the measure of E is 0. Okay? Now, this I have to give credit. This is called Borel-Cantelli lemma. If you have a sequence of sets whose measures are summable, then almost any point belongs only to finitely many of those sets. The set of points x that belong to an infinite number of those sets has measure 0. Okay? So what did I prove here? I proved that for any positive epsilon, the lim sup 1 over n phi fn of x is less than epsilon for mu almost every x. Now you take epsilon 1 over j going to 0, and you conclude that lim sup of 1 over n, taking the intersection, lim sup of over all these j over all these epsilons is less or equal than 0 for mu almost every x. You have a full measure set that satisfies this for epsilon equals 1 over j. For every j, you take the intersection of all over all j. That gives you a full measure set where you have this. And of course, lim sup being less or equal than 0 for a non-negative function is the same thing as saying that the limit is equivalent to saying that the limit is 0. Okay. So instead of using the ergodic theorem, you use Borel-Cantelli. In order to use Borel-Cantelli, you need to know this, and this you deduce from the assumption that phi is integrable, and I'm not going to do that because we all want to have coffee. This is an exercise. Okay? And then you go back to the place where I was in the proof of the subadditive ergodic theorem. You realize that lemma 1 is okay, is sufficient. Okay? That's all for today.